So thus far, we've talked about 4 different gas laws: Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. And each of these laws enabled us to anticipate what would happen to a certain property of a gas if we changed its conditions, like changing pressure, volume, or temperature. Now we're going to combine all of our variables together in what is called the ideal gas law. Now, what the ideal gas law allows us to do is to relate pressure, volume, number of moles, and the temperature. So the equation for the ideal gas law is the following: PV equals nRT. Okay, so let me quickly go through each of these variables just to quickly review what each of them is. So P is my pressure. And the units for pressure in my ideal gas law have to be in atmospheres. And I'll explain why in just one second. My next variable is volume. My units for volume have to be in liters. N is my number of moles. R is what we call my ideal gas law constant. Now this will always be given to you, but the value for that is 0.0821, and here are where the units come in. Okay? My units are atmospheres times liters over moles Kelvin. Okay, so that is why my pressure has to be in atmospheres, my volume has to be in liters, number of moles is moles, and my last variable here is my temperature. And notice, based on my ideal gas law constant, temperature has to be in Kelvin. All right, so what this equation allows me to do is say, okay, if I know the volume, the number of moles, and the temperature of a gas, I can figure out its pressure. Or if I know the pressure, the number of moles, and the temperature, I can figure out the volume. All right, so let's look at a couple of examples here. Example 1 says, if I have an unknown quantity of gas at a pressure of 1.2 atmospheres and a volume of 31 liters and a temperature of 87 degrees Celsius, how many moles of gas do I have? So I'm solving for N. 1.2 is my pressure. This is my volume, 31 liters, and my temperature is 87 degrees Celsius. So let's plug and chug. So PV equals nRT. Remember, my pressure has to be in atmospheres, which it is, 1.2. My volume has to be in liters, which it is, 31. I am solving for my number of moles, that's my N. My R is my gas law constant, 0.0821. Okay. And finally, my temperature needs to be in Kelvin. And so what I need to do is I need to take 87 and I need to add to that 273 to convert into Kelvin, just like we did before. And what I get here is 360. And I'm going to make that 360 point simply because when I round this value, I want to make sure I have no decimal places, but I want all 3 of these digits to be significant. Okay, so what am I going to do? I'm going to first multiply out. So I've got 1.2 times 31, and what I get here is 37.2. So 37.2 equals my number of moles times, I'm going to take 0.0821, and I'm going to multiply by 360. And what I get here is 29.556. Now all I need to do is divide both sides by 29.556. And unrounded, I get 1.259. So my number of moles equals 1.259. Okay, let's figure out sig figs. 1.2 has 2 sig figs, 31 has 2 sig figs. These both have 3, but I want to round to my fewest number sig figs. So this will simply round to 1.3, and my units are moles. So 1.3 moles. All right, let's look at the next practice problem. If I have 40 moles, so now I'm being given my number of moles, my N, of a gas at a pressure of 4,256 millimeters of mercury, so that is my pressure, and a volume of 12 liters. Okay, if I have that, what is the temperature in degrees Celsius? So I'm solving for T. Okay, so let's plug and chug. PV equals nRT. All right, my pressure right now is in millimeters of mercury, but remember for my ideal gas law, I need to be in atmospheres. So I'm going to take 4,256 millimeters of mercury, and I need to first convert that into atmospheres. So I'm going to get out of millimeters of mercury by putting it on bottom. I'm going to get into atmospheres. I know that 1 atmosphere is 760 millimeters of mercury. And so what I get for my atmospheres, I'm going to take 4,256, I'm going to divide by 760, and what I get is 5.6. Now keep in mind, to keep with the correct number of sig figs, this should be 1, 2, 3, 4 sig figs, so 1, 2, I'm going to add 2 zeros to this, but that is my pressure in atmosphere. So now I can plug it into my equation, so 5.600. I know my volume is 12 liters. In this problem, know my number of moles, it's 4.0 moles. My R is my gas law constant, 0.0821. And then I'm going to solve for my temperature. Okay, so I'm going to take 5.6 and I'm going to multiply it by 12. And what I get is 67.2. Okay. That equals, I'm going to take 4.0 and multiply it by 0.0821. And what I get is 0.3284. Okay, and I'm going to multiply that by my temperature. Now I need to divide both sides by 0.3284. Okay, so I'm going to take 67.2 and divide by 0.3284. And what I get from my temperature is 204.6. Now keep in mind, you might be tempted to just box this off and be done, but remember the temperature in your ideal gas law is in Kelvin. But notice the question is asking for it in degrees Celsius. So to get into degrees Celsius, remember your temperature in Kelvin equals your temperature in Celsius plus 273. So if I'm already in Kelvin, then to get into degrees Celsius, I just need to subtract by 273. Okay, and so when I do that, what I get is negative 68.4. Remember, my last step here is subtracting, so I need to round based on decimal places. Well, 273 has no decimal places, so negative 68.4 should simply round to negative 68, and my units are degrees Celsius. All right, let's look at the next practice problem. If I have an unknown quantity of oxygen gas held at a temperature of 922 degrees Celsius in a container with a volume of 25 liters and a pressure of 560 atmospheres, how many grams of gas do I have? All right, let's write out my ideal gas law again. Keep in mind here, this is my temperature, this is my volume, this is my pressure. So right now, even though the question doesn't state it, I'm going to be solving for moles first. Once I know my number of moles, then I can figure out the grams of gas that I have. Okay, so I know my pressure is 560 atmospheres. All right, I want to be in atmospheres, I'm good with that. My volume is 25 liters, I want to be in liters, I'm good with that. I'm going to solve for N. My gas law constant is here. And then for my temperature, it has to be in Kelvin. Right now, I'm in degrees Celsius, so I need to take 922, add to that 273, and what I get is 1,195. Okay? So to solve this, I'm going to take 560 and multiply by 25. And what I get is 14,000 equals n times 0.0821 times 1,195, and I get 98.1095. Okay, and then I'm going to divide both sides by the 98. And what I get is 142.7. So my number of moles is 142. And I'm going to round here, but I'm going to keep the unrounded value in my calculator. All right? Now I'm in moles, but it asks for my value in grams. So what I now need to do is get out of moles, and I need to get into grams. Okay? Remember, this goes to way back when, but remember, to go from moles to grams, I need to use my molar mass. Well, the identity of my gas is oxygen. So I've got oxygen with a molar mass of 15.999, but there are 2 of them, so I'm going to multiply by 2, so I get 31.998. So that is the molar mass of O2, 31.998 grams for every 1 mole. So I'm going to take the value that I kept in my calculator and multiply it by 31.998, or you can simply retype it if you want to, but don't round to 142.7. Keep the whole unrounded value in there. And so what I get for my mass, unrounded, is 4,566 grams. Keep in mind, though, let's figure out sig figs. 560 has 2 sig figs, 2 sig figs, 3 sig figs, 1, 2, 3, 4 sig figs. So I need 2 sig figs, 1, 2. So this is going to be 4,600 grams. All right, last practice problem. What volume, so I'm solving for V, does 8.56 moles, that's my N, of a gas occupy at 21 degrees Celsius, that's my temperature, and this pressure? All right, so I'm solving for my volume. I'm going to use my ideal gas law again. Okay, keep in mind my pressure needs to be in atmospheres, but right now it is millimeters of mercury, so I need to convert this. I'm going to get out of millimeters of mercury and into atmospheres. Okay, I know that 1 atmosphere is 760 millimeters of mercury, so I'm going to take 750 divided by 760, and I get 0.9868. Now I'm going to keep the unrounded value in my calculator and just plug that in when I'm actually doing my calculation, so I'm not over rounding. But since I don't want to write the whole thing out here, I will just round this. Okay, my volume is what I'm solving for. That equals my number of moles, which is 8.56, times my R, which is 0.0821. And then my temperature is 21 degrees Celsius, so I need to add 273 to that to get that into Kelvin. So that's going to be 294. All right, so now what I need to do is I'm going to multiply 8.56 times 0.0821 times 294, and then I'm going to divide that by my 0.9868, but the whole value that I have in my calculator. So I'm simply going to divide by my answer. And what I get is 209.37. So my volume is 209.37. Okay. Keep in mind, let's figure out sig figs first. I've got 1, 2, 3, 4 sig figs from here. 21, I'm going to base my sig figs off of 294. So that's 1, 2, 3 sig figs there. 3 sig figs from 8.56. So I should have 3 sig figs. So this will simply round to 209. Keep in mind, my units for volume using the ideal gas law are going to be in liters. I'm good to go.
And what we're going to do now is we're going to use your ideal gas law and learn how to determine the molar mass of a gas. All right, so in this problem, it asks what's the molar mass in grams per mole of a gas if a 3.16 gram sample of gas at 0.750 atmospheres and 45 degrees Celsius occupies a volume of 2.05 liters. So this problem might seem super complex until you realize you're going to be having two different problems. The first problem you're going to do is you're going to be using the ideal gas law in order to solve for moles. So you're going to use your pressure, your temperature, and your volume to solve for moles. Once you know your moles, in order to get into molar mass, which by the way, the units are grams per mole or grams divided by moles, all you have to do is take your mass, which was the 3.16, divided by the number of moles that are involved, and that'll give you your molar mass. So let's actually do the problem. So I'm going to use PV equals nRT. I have my pressure already in atmospheres. I have my volume already in liters. I'm solving for N, my number of moles. I know my R is 0.0821. And my temperature right now is in Celsius, so I need to convert that into Kelvin by simply adding 273. So I plug in all of my values. Okay? I'm going to take 0.750, multiply it by 2.05. Then I'm going to divide whatever I get for that product by 0.0821, and then I'm going to divide that by 318. And what you get is your number of moles, which is 0.05889 moles. Now that I have my number of moles and I have my mass, you can determine your molar mass. All you have to do is take your mass, 3.16, divide it by 0.05889. That will give me grams per mole. And so what I end up getting for my molar mass is 53.7 grams per mole once I take into account significant figures. Okay, so the only thing that I've added to this problem, the only reason why this is slightly different from just an ideal gas problem, is the fact that I'm now asking you to take your moles and apply it specifically in order to determine your molar mass. And in order to do that, all you have to do is take your mass, divide by the moles that you calculated, and there's your molar mass.
So in addition to using the ideal gas law in order to determine molar mass, we can also use ideal gas law and density in order to determine the molar mass. So if we look at this question, it says, what is the molar mass of a gas with a density of 3.50 grams per liter at a temperature of 345 Kelvin and a pressure of 0.950 atmospheres? So the hardest part about this problem, ultimately, I'm trying to get into grams per mole, which is my molar mass. And if you notice here, I tell you the density, 3.50 grams per liter. And at first you might be freaking out about those units, but all that is telling you is actually that you have 3.50 grams in 1 liter. So 3.50 grams of that gas has a volume of 1 liter. So what I'm going to do is I'm going to use my ideal gas law, PV equals nRT, and I'm going to assume that the volume I'm using is 1 liter. And I'm going to plug in all of the values that I know in order to solve for moles. Okay, so to do that, I know my pressure is 0.950. I know my volume now is 1 liter. Okay. I'm going to be solving for N. I know my R is 0.0821, and I know my temperature is 345 Kelvin. So now I can solve for my number of moles, which is 0.0335 moles. Now another way of saying that is that I have 0.0335 moles in 1 liter, right? Because my volume is 1 liter. Or I could say that's 0.0335 moles per liter. So if you notice, I have 3.50 grams per liter, and I have 0.0335 moles per liter. So if you think about it, all you need to do to get into grams per mole, which is what I'm trying to do, get into molar mass, is I need to divide 3.50 by 0.0335 moles. Notice the liters will cancel and my final units will just be grams per mole. And so the answer I get for my molar mass here is 104.35 grams per mole. So you can use the ideal gas law in order to determine molar mass if you're given the mass or if you're given the density.
So in this final section, what we're going to do is we're going to apply the ideal gas law and now incorporate stoichiometry into that.
So in all reality, none of this is new. It's just applying things that you've already learned and combining things together. So it's actually really cool because you're being able to use skills from other lessons, other units in order to bring everything together. So we're just going to be looking at a problem in order to make sure you understand this. So if it tells me I have 12.8 grams of aluminum and it reacts with hydrochloric acid, HCl, this is asking me how many liters of H2 would be formed at 715 millimeters of mercury and 19 degrees Celsius. So ultimately, what it's asking me to do is say, okay, I have 12.8 grams of aluminum. How many liters of H2 would be formed? The issue here is you've actually learned how to do this. The problem in this problem is that you're not at standard temperature and pressure. So you can't use the relationship between liters and moles that we learned, which is that 22.4 liters equals 1 mole. So instead, since you have a pressure and a temperature that are not standard temperatures and pressures, you're going to be having to use your ideal gas law. But in order to use my ideal gas law, which ultimately what I'm going to want to do is figure out the moles of H2 and then be able to apply that to my PV equals nRT equation. I have to figure out first the reaction between aluminum and hydrochloric acid and then be able to do the stoichiometry to convert between grams of aluminum and get myself into moles of hydrogen gas. So I first have to write out the reaction. So I know aluminum reacts with hydrochloric acid and it's going to produce, remember this is a single replacement reaction, so aluminum is going to go in and it's going to kick out the hydrogen because the hydrogen has a positive charge. So Al and Cl are going to combine together. Aluminum has a +3 charge, chlorine has a -1 charge, so that's going to become AlCl3 and hydrogen gas. Now the issue is, if you notice, I'm going to want 3 Cl's and 2 H's based on what I have in my products. The only thing they have in common is 6, so I'm going to put a 6 in front of HCl to balance that out. I'm going to put a 2 in front of AlCl3 in order to get those 6 chlorines. I now need a 3 in front of H2 in order to get 6 hydrogens. And finally, I'm going to put a 2 in front of aluminum, so I have 2 aluminums on my reactant and product side. Now that I'm balanced, I can do the stoichiometry to figure out how many moles of hydrogen gas I have. So I'm going to start with 12.8 grams of aluminum. I'm going to convert that first into moles of aluminum because in order to go from terms of one reactant into terms of a product, I've got to use my mole to mole ratio. And in order to do that, I've got to be in moles of aluminum. So I'm going to put grams of aluminum on bottom, moles of aluminum on top. I have 1 mole for every 26.982 grams of aluminum, since that's the molar mass of aluminum. I'm now in moles of aluminum. I'm going to get into moles of hydrogen. So I'm going to put moles of aluminum on bottom, moles of hydrogen up top, and that ratio is based on the coefficients, so it's going to be 3 to 2. And now I can figure out my moles of hydrogen because those are the units I'm in. So I'm going to take 12.8, I'm going to divide by 26.982, and then I'm going to multiply that by 3, which is the moles of hydrogen, and divide that by 2. Okay? And so that equals 0.71159 moles of hydrogen gas. So now I have my moles of hydrogen gas, I know the pressure of my hydrogen gas, and I know the temperature of my hydrogen gas. And so what I can do is now use PV equals nRT and solve for the liters of hydrogen. The only issue is because I have 715 millimeters of mercury, I first have to convert that. I'm going to take that, put atmospheres on top, millimeters of mercury on bottom. When I divide, I get 0.94079 atmospheres, and now I can use that pressure in my ideal gas law. So it's going to be 0.94079 times my volume. Well, I don't know what that is, so it's going to stay as V. That equals my moles that I just solved for, 0.71159, times my R, 0.0821, times my temperature. Remember, temperature, I just need to take 19 degrees Celsius and add 273 to that. Okay, and there we go. So I'm going to take what I have on my right-hand side, multiply them all across. Then I'm going to divide by 0.94079, and that gives me my volume, which is 18.1 liters.
So another situation that we could be in is rather than being, for example, in the problem you just saw, at a pressure of 715 millimeters of mercury and 19 degrees Celsius, you could be at standard temperature and pressure. And so that's going to change the problem. It's actually going to make it easier. And the reason why it makes it easier is it lets us use a relationship that we haven't quite talked about. So let's look at the relationships with regards to moles that we have talked about. So first of all, we know that 1 mole of a substance equals the molar mass of that substance in grams. So for example, if I have 1 mole of oxygen, O2, I know I have 32 grams of oxygen. And that's why the unit for molar mass is grams per mole, because there are that many grams for every 1 mole. Another relationship that we know is Avogadro's number. So we know, for example, if I tell you, hey, I have 1 mole of nitrogen, you know I have 6.02 or 6.022 times 10 to the 23rd particles. That could be, so in that case, that would be atoms, but it could be atoms, it could be molecules or formula units. So if I have 1 mole of carbon dioxide, I would have 6.022 times 10 to the 23rd molecules of carbon dioxide. Now there's one other relationship that I'm now going to introduce, and that only occurs for gases, and make sure you know it's just gases. It does not apply to solids, liquids, or aqueous solutions. For gases that are at standard temperature and pressure, and remember, standard temperature and pressure is 1 atmosphere and 0 degrees Celsius. So the example problem we just did would not work because I'm not at STP. But if I am at STP, then I know that 1 mole of that gas has a volume of 22.4 liters. So it could be 1 mole of oxygen, it could be 1 mole of carbon dioxide, it could be 1 mole of nitrogen, it could be 1 mole of fluorine. It doesn't matter the identity of the gas. If I have 1 mole of it and I'm at standard temperature and pressure, so a specific pressure, a specific temperature, every gas will have a volume, ideally, of 22.4 liters. So the reason why I introduced this is because now instead of having to use our ideal gas law, PV equals nRT, what that allows me to do is simply to use this volume, 22.4, as a conversion factor, so you no longer have to use PV equals nRT.
So let me show you what it would look like if I were at standard temperature and pressure, because for some of the problems I'll give you, you'll stay at STP, so it'll be a really nice, easy problem. So the setup at the beginning is going to be the same. Notice it states in the problem I'm at STP, so this is the only time you can do this, is if you're at STP. So you're going to go from 12.8 grams of aluminum, put grams of aluminum on bottom, moles of aluminum up top, okay? 1 and 26.982. Now I'm in moles of aluminum, just like the problem before. I'm going to get into moles of hydrogen, so moles of aluminum on bottom, moles of hydrogen up top, put a 3 and a 2. At this point, that was when I had to plug in my moles of hydrogen, whatever you got from this, into PV equals nRT because I was not at STP. But since I am at STP for this problem, what I can do is put moles of hydrogen on bottom, liters of hydrogen up top, and just say 22.4 liters equals 1 mole. So this problem is a lot easier because I don't actually have to plug it into the ideal gas law. And what I get for that is 15.9 liters. So the main thing for you to know is if I'm not at STP, I have to use the ideal gas law in order to figure out volume or whatever it's asking for. If I am at STP, I can simply use the fact that 22.4 liters equals 1 mole when I'm at STP.